from Budapest who talks on Boolean functions defined on pseudo recursive sequences. Yes, please.
Thank you. To start, first, I thank for the possibility to speak here, also only via Zoom. So the question is that, what is the reason that I investigated pseudo recursive sequences? The first motivation is the subset sums, the notion of the subset sums. It is defined in the following way. We have an X is a subset, mainly an infinite subset of the positive integers. And the subset sum is defined in the following way. We find the infinite sequence of variables, epsilon I. They are 0 or 1. And only finite many epsilon equals 1. And if you consider the finite version of this notion, so X is a finite set, assume that the cardinality of it is n, then one can consider it as an image set of a Boolean function on the Boolean cube 0, 1 to the n. More precisely, if X is a finite, then we can define a function. So we have a 0, 1 sequence, epsilon I, epsilon 2, and so on, epsilon n, when the form of this function is the summation epsilon I xi modulo 2. It is said to be Boolean function, but sometimes there is another definition when from 0, 1 to the n to the real numbers. This function is linear and well-known, and one can describe it in a simple way, so it is not too interesting. So it is the reason that we modify a little bit the form of the function will be a multilinear function. So the second motivation is the notion of the pseudo-recursive or linear. So I will consider just linear sequences in the following form. So the first X naught is the first element. It is arbitrary positive integer. And we have an infinite sequence of integers, which is a non-decreasing sequence. And there is another set, that finite set, B1, B2, and so on, Bs. And we create the following recursion. So xn plus 1 is equal to m subscript n plus 1, xn plus b jn plus 1. So it is what we can vary. And I merely investigate just when all mi is a fixed positive integer, let us denote it by m. So it is the recursion, and do not forget that this term can be different in each occasion. Essentially, I will show you that it is a bracket sequence. So as an intermezzo, in this slide, I recall some interesting questions related to the bracket sequences. Just a definition, as we have seen in the first day, subset of the integers is said to be complete if the subset sums cover almost all, so just finite many exception the integer, some complete if it contains an infinite arithmetic progression, strongly complete if X remains complete after any finite number of terms have been deleted from it, and strongly some complete in a similar way. And I recall here some old questions. Erdős problem was the following. if we have integer t and a real number between 1 and 2, then create this bracket sequence. What about the behavior of it, taking the question of complete behavior? Graham showed in 64 in the past millennium that if t is 1, that it is complete if and only if alpha lies in the given interval. A little bit later, Erdős and Graham asked the following: is it true that if we have the following sequence, A alpha beta, so we take the integer part of alpha, beta, the double of alpha, double of beta, sorry, he missed the 2, and so on. So 2 to the n times alpha, 2 to the m times beta, integer part. And the question was that, is it true that it is complete? And they conjectured that it is true. Then if the ratio of alpha and beta is an irrational number, I investigated this question a couple of papers, and I believe that it is enough that the ratio is not a 2 power. I list some results for this type of question. So I show that A alpha beta is complete if we express alpha in a binary form, then alpha is a finite diadical fraction, means that it contains finite many ones, and beta is infinite diadical fraction. And furthermore, I showed that it will be complete if we have additional term, namely a gamma, in the reasonable way, provided that one of the alpha, beta, or gamma is an IDF. And I mentioned just only another result, that I showed that there are continuum many pairs of alpha, beta, for which this set is not complete. So it is just the reason that it is interesting for me. Okay, so instead of a linear function, what I introduced in the beginning of my talk, I introduce, okay, I can describe the function defining hypergraphs. So the first, what I consider it is a k-uniform cycle hypergraph with k minus 1 many common elements in the connected edges. So it will be the first function. I denote it by f subscript alpha, and the variables are 0 or 1, x1, x2, and so on, xn. And this addition is the XOR, which means that the addition considered in mode 2. And the coefficients are from the indicated bracket sequence. So firstly, I mentioned that it is not the usual Boolean form of the function. So it is a little bit different one, because first I define in the integer, and after I take the mode 2 value of it. So it is well defined in some sense, but not the Boolean form. It is my first remark. And the second, that one can consider the support of this function, support that actually where the value is odd, so when the value is 1. And it is not too complicated to determine. If you express alpha in base 2, then it is not too hard to see that the A1, A2, and so on is just the digits of the sequence. So in this form, it's not too hard to detect what is the cardinality of the support. If you have a block of the digits. So if you take k many consecutive elements, and if you add these digits and it gives an odd number, then fix, okay, so the starting element, the subscript of the starting element is I, then let us fix the variable xi, and you can switch the value to the other one if the given substitution is 0, and it is not too hard to see that it turns to 1. Therefore, the cardinality of the support is 2 to the n-1 in this case. So the challenging problem is the Fourier spectrum of f alpha. And the link between the spectrum and the binary expansion is as I mentioned before. So I denoted by capital M those subscript when if we take the binary expression of alpha and the number of blocks, so that the starting element of the blocks, when the summation of the digits is an even number, and let us denote it by small m, the cardinality of this set. And do not forget that it is a cycle hypergraph, so alpha s is the same than alpha t when they are congruent modulo. And so to take f alpha, one can use elementary Fourier analysis. I list here. So the expectation is actually the average, here the inner product, and there is a 1-to-1 map between the subsets and the element of the 0, 1 to the n. And here the basis function or the characters are -1 to the inner product, and the Fourier transform defined in this way. Without proof, I mentioned here just my first proposition. So if I lies between k and n, then one can characterize those subsets where the Fourier transform is 0, namely that assume that S contains the element I, then this Fourier transform is 0 if and only if the subscript belongs to M. We can derive this statement from the second proposition. Here I define the influence of the function. The influence is actually the probability that if we switch the i's position of the variable to the opposite, then what is the chance that the function differs from the previous one? Okay, the next function what I would like to define is a little bit different, because here the map is not to the 0 one, rather all real numbers. Sometimes it is also said to be Boolean. Not too hard to see that if this bracket, so the coefficients is the integer part of 3 to the I to the times alpha. And first of all, it is not too hard to see it as elementary, easy by induction that they are different. Therefore, there is a 1-to-1 map between the image set and the set where it will be -1 or 1. Not too hard to see that the image set is at most 2 to the R, and not necessary R equality here is an example. And the theorem says the following: it is epsilon thing. If I remember, I did not define it. So epsilon thing is the system if we consider all intersections of Si as J. I differs from J, and the cardinality of them. If I add them, then it will be at most epsilon times R. So in this case, the image set is almost what we want. The proof is not too hard, namely that here is the representation function can be calculated as V. It denotes the 0, 1 to the R. So it is 2 to the R actually, and we consider the maximum representation function that it is enough to prove that the representation function always at most 2 to the n minus R plus epsilon R. And here is the simple proof. Then let us denote by delta is the union of all intersections. And let us fix them. The number of tuples can be calculated in this form. We can have 2 to the delta many values of the restricted parts. So therefore, it will be the representation function can be bounded by 2 to the delta from here. And from here, we have 2 to the S prime, cardinal S prime minus 1, and it gives what we want. Okay, the rest of my talk is a little bit more sophisticated in the sense that let us call again what is the influence. So the influence means that if we switch the i's, so we take the i's position of the variable and we switch to the opposite one, then what is the chance that it turns to the other one? So one can believe that if the total influence is the sum of all possibilities, and someone believes that someone can believe that if it is not too big, then the support should be structured. So some sense it is composed by some blocks, and it is true. So low influence implies that the support is structured. So here is the main theorem of my talk, that if I denote it by capital A, the support of it, then there exists a subset of it, which is big in the sense that it is at least the cardinality, the proportion of the influence of the original cardinality, such that A star is contained in a coset of this structure, such at most, which is written here. So it is okay. So I should say that when the influence is less than ace root of the logarithm, then it is not meaningless. So it is, say, it is a constant or very slow of the function of A. Then it is structured as we expected. So here some lemmas. The first is well known. If we take the force moment of the function, that it will be the 1 over 2 to the 3m times the additive energy of the set. Additive energy means that we count all 4 tuples of A when the addition of A1 plus A2 gives the same that A3 plus A4. And here is the here is the next statement. I checked my time, so I have not too many. So I will. Okay, here is the statement. So the total influence is for all s, the coordinate of s times the square of the Fourier transform. I omit the proof here because it seems to me that I have not time enough. And the main, what I would like to show you, that the main uncertainty inequality, it says as follows, that if we have a Boolean function and A is the support or the inverse image of the one, and EA is the additive energy, then the additive energy times the influence can be bounded below the A cube, the coordinate of the cube of the coordinate of A over T. The short proof is the following: by the Parseval equality, the second moment is A times the coordinate of A times 1 over 2 to the n, and we take the truncated form of it. So we consider we cut two parts, and this part will be alpha times the influence. And by the Cauchy inequality, we have this form, and after we can, it's an elementary bound that we have, that it can be bounded in this form. Therefore, coordinate of A over 1 over 2 to the n can be bounded this form. And as usual, the first term is a decreasing, the second term is an increasing. As usual, when the two terms are the same, then we get the bound. So we calculate alpha here, and it gives this form, which give the, taking the cube, we obtain the result of the uncertainty equality. And I recall two lemmas. The first is due to Thomas Schoen. It sounds as follows: if A is a subset of the F2 to the n, and suppose that the additive energy is that kappa times A cube, the coordinate of A cube, that there exists a subset when it is containing coset this one. The second, so for every subset we have this one. The next result is due to Sanders. So this is my lemma, and here is the statement of, sorry, so it is my statement, and it is composed by two results by Schoen, that if the additive energy is kappa times a coordinate of A cube, then it contains, it's something like that. And the next one is due to Sanders, when if we have a subset of the F2 to the n, and we have this one, then it is contains. So this does with, if we choose K to the kappa to the -4, we obtain the lemma. The theorem then follows with 1 over the influence, and it is easy to check. Here I list an appendix, but it seems to me that I have no any time to. Okay, one minute. Just I recall the problem only. That so the question is the following: that we have an additive structure, say F2 to the n or something else, so finite fields or something like that, and we consider all subsets where the additive energy is at most coordinate 3 minus eta. Capital, so the coordinate of A to the 3 is the bound of 80. So it's a little bit less than the trivial bound, the trivial upper bound. So we consider all sets, and we want to know that what is the biggest fulfills this condition. And for example, when it could be when eta is 1, then it would be 1/2, since for the Sidan sets we have this one. So here the eta is 1, and S is square root p. I investigated a similar question, f2 to the n, and I obtained this form at the time. I should say that it is not necessarily the optimal. I calculated by hand. So thank you for your attention.
Thank you, Norbert. Are there any questions for our speaker?
Okay, I lost you. No.
No.
Okay, what can I? How can I stop the?